Okay, so in the last video, we talked about the idea of energy degradation, which basically means that anytime you do anything, any type of mechanical process, um, you always have some energy loss due to heat, which is the same thing essentially as saying that you cannot have any process that is 100% efficient. Now, we know from last year you cannot have anything more than 100% efficient because that would, of course, violate conservation of energy. You can't get more energy out than you put in. But this new idea coming from the second law of thermodynamics says, wait, you can't even get to 100% efficiency because anytime you do anything, you always have some heat loss, some energy loss. Okay, and so that is the principle of energy degradation. We say degradation meaning the energy is degraded because once it becomes heat, even though that energy still exists in the universe, heat is a less useful form of energy because um, you can't do very much with it. Okay, so just to give you an idea, if you lift up a weight and then you drop the weight onto the ground, um, as you lift the weight, you give it gravitational potential energy. The weight falls, it gains kinetic energy, and when it collides with the ground, it transfers all of that energy into heat. Okay, but that heat is just in the ground. Okay, you can't really do anything with it. You can't. It's not like you can magically take that heat and put it back into the object and have the object float up into the air. That would not violate conservation of energy per se, but it would violate the second law of thermodynamics because heat is the less useful form of energy. And so to kind of visually indicate this energy degradation, we have what's called Sankey diagrams, which are basically energy flow diagrams. And so that's where we left off at the end of the last video, is looking at these Sankey diagrams. So Sankey diagrams are basically drawn with arrows, um, and the way these kind of diagrams are drawn is normally on the far left, you start with all of the energy you have, and at each stage you kind of see energy transforming from one form to another. The degraded energy, you can see these yellow arrows kind of split off and go towards the bottom. That is usually how the degraded energy is indicated. And so, for example, here we see chemical energy, 100 megajoules. Up here we see potential energy, 80 megajoules. That means this yellow arrow represents the energy lost in that transition, which would be 20 megajoules. And so this 20 megajoules is being converted to heat or wasted as heat there. We've talked, of course, about efficiency in the past. Efficiency would be output over input. And so going from chemical energy to potential energy in this situation would be like 80 over 100, which would just be 80% efficient. Okay, and so we'll talk about some key elements of Sankey diagrams and how to draw and interpret them. But take a look at this picture, and it says which process is more efficient. Okay, so we've got two Sankey diagrams, and nothing is labeled, but just based off of how the arrows are drawn, which of these processes is more efficient, the one on the left or the one on the right? Okay, well, remember efficiency is output over input. The input appears to be the same because the width of the starting arrow is the same in both pictures. The output is shown by the arrow going to the right. And so if you look at the thickness of the output here versus the output here, you can see there's clearly more output over here. Okay, meaning that this is the one that has the higher efficiency. And then those downward arrows indicate energy degradation at different stages. Okay, as you can see here. All right, so let's talk about some rules for drawing and interpreting Sankey diagrams. Um, First of all, each energy source and loss is represented by an arrow. If the arrow is going to the side, or sorry, if the arrow is going up or down, that is usually energy loss. When you're drawing Sankey diagrams, the length of the arrow does not make any difference, but the width of the arrow is proportional to the amount of energy represented. Meaning if you have an arrow twice as wide, that typically means twice as much energy. Okay, but the length doesn't matter. A lot of the time when you're doing Sankey diagram problems, the IB gives you like grid paper to do these problems on so that you can make sure to draw them proportionally correct. okay, because again, the width does matter. And energy flow is normally shown from left to right. There are some examples in the textbook, but we can take a look at some examples here. So here you can kind of see a Sankey diagram, um, and you always read these from left to right with the energy input being over here. The downward arrow represents the wasted energy or the degraded energy in the form of heat, and the output energy is represented by going to the right. The length does not matter, but the width is important. And so, for example, let's say if I wanted to find the efficiency of whatever process this is, then I would have to say, okay, so there's 5, 10, so that's 15, so there's 20 boxes. And so the input has a width of 20 boxes, and the output over here has a width of 6 boxes. And so the width is proportional to the actual energy. And so even though I don't have any numbers, I can tell just from the width that the efficiency of this process would be 6 over 20, which would be 30%. And so if you were given the Sankey diagram, you would be expected to know or to be able to figure out what the efficiency is, or vice versa, if you were given the efficiency, and let's say they only give you like the left side of the Sankey diagram, you would be expected to draw the other side of the Sankey diagram so that you know, the width was correct for that given efficiency. All right, so pause there if you need to look at that some more. And let's take a look at some examples. Okay, so example 1 says, use the Sankey diagram to the right to calculate the efficiency of the lamp. So based off what we have been talking about, go ahead and do example 1 on your own. Okay, so here you can see the input is 100, the output is 75, so 75 over 100 represents 75% efficiency. And then the 25 joules is energy that is degraded in the form of heat. Okay, so really simple example there. All right, so this is a simple IB question. Here they don't have the degraded arrows going up or down, they have them going up for some reason. I don't know why, but so the question says the diagram below shows an energy flow diagram, aka a Sankey diagram for a car, and it's basically asking what is the efficiency of the car. Okay, so pause it here and try to answer this question on your own. Okay, so of course the answer there has got to be A. Again, efficiency is output over input. The output is here, the input is here, and so that is 30 over 100, which is 30%. Okay, so whether the arrow is going up or going down, it still represents the degraded energy, okay, degraded in the form of heat. All right, so let's take a look at one more example. Example 2, it says using the Sankey diagram for a thermal power station shown to the right, determine the energy which becomes electrical energy and the energy which becomes wasted. All right, so we have the Sankey diagram here, and it's probably a little hard for you to read, but it is on a grid, and so we know that the input is 5,000 joules. The first question is asking how much energy becomes electrical energy. So looking at the width of this arrow over here, I can kind of see how many boxes that is, and it looks like it has a width of 9 boxes. Okay, the original arrow over here, if you count the boxes, that's 5, 10, 15, 20, 25. Okay, 1, 2, 3, 4, 5. Yeah, 25. All right, so that means the efficiency would have a ratio of 9 over 25, which is 36%. Which means that if the input is 5,000 joules, we can calculate the electrical energy, because the electrical energy would just be 36% of that 5,000 joules. All right, and so this is kind of showing you a slightly more complicated Sankey diagram example. Honestly, Sankey diagram problems are not really difficult, but this is just showing you something a little different than what we've seen before. That would be 1800 joules, and then we want to know how much is wasted. Um, well, of course, that would be everything else, so that would be 5,000 minus 1800, which is 3,200 joules. That's wasted. Now, you do need to be careful on these problems because notice you have energy being degraded in different ways at different steps of the process. And so here it's kind of ambiguous as to whether they mean like wasted like overall or wasted in different processes that is happening. So just kind of watch out for that. And this is just like a really super complicated Sankey diagram, just showing the energy energy use for our country. Um, yeah, you're not going to have anything this complicated on any of your questions, but just to kind of show you, Sankey diagrams can also be kind of scary. All right, so let's talk about fossil fuels. So fossil fuels and why we can't live without them. All right, so fossil fuels are a non-renewable energy source. In the sense that the rate at which we are using them um, is less than the rate at which they're being produced. Over time, people have been really worried about running out of fossil fuels, um, especially over the last 100 years. We've kind of been getting nervous about that, but then what seems to always happen is that new technology will be developed, which actually gives us more access to the fossil fuels inside the Earth. And so the answer to the question, are we running out of fossil fuels? It's kind of hard to pin that down because every time we go to say yes, we come up with some type of new technology or new method to increase our access to fossil fuels. And so the answer to the question is yes, but we probably have more than some people think. We're not going to imminently run out of fossil fuels in the next couple of years. Okay, we potentially have enough to last us for several decades, if not several hundred years, and that time frame could always like increase as we develop new technologies. Okay, so for example, um, over the past few decades, we've developed new methods of drilling, as opposed to what we used to do back in the old days, where we just put like an oil well like down straight into the ground. Now we're doing more like horizontal drilling, where we kind of drill down and then we drill like sideways, and it gives us access to way more oil than we had previously. Okay, just a fun quick question. Look at these different countries. Who do you think is the largest importer of oil to the US? Okay, you actually might be surprised. The answer is actually Canada. And I know there's always like a lot of focus in the news um, about the Middle East, especially like Saudi Arabia. Um, but we actually get a lot of oil from Canada, which always surprises a lot of people, but they're closest to us, so that kind of makes sense. And in fact, you can kind of see on this chart, this is from 2017, the different countries, and relatively speaking, how much oil we get from those different countries. Now, of course, the US also has a lot of oil reserves on our own. Here you can kind of see some different charts. It's kind of hard to read what's on the chart. Um, but you can kind of see like in terms of like million barrels, the darker colors are where we have the most oil. And so obviously in Texas we have, millions, or really billions of million barrels of oil um, within Texas, which is one reason why Texas is really self-sufficient in terms of its oil production. And different states have access to different amount of oil. But out of all the states in the country, Texas has the most oil available to it. Now, we kind of talked about this before in the last video when we briefly talked about thermal power stations. We talked about electromagnetic induction. Um, but let's just really quickly describe how fossil fuel power stations work. Okay, so the most common way to generate power is through, burning fossil fuels. Now, usually we don't burn oil because we have better uses for oil than burning it. Okay, but coal and natural gas we can burn. Okay, in fact, a lot of people, including myself, in our houses, we have natural gas, and that is what we use to use our stove or heat our water or have like hot air in the wintertime. Okay, that comes from natural gas. Um, but if you're talking about like power plants, coal power plants and natural gas power plants work in a very similar way. You burn these things, and the burning releases chemical energy in the form of heat, and that heat is used to boil water, and the water, of course, turns to steam. The steam pushes on a turbine. The turbine is connected to a generator which has coils of wire spinning around a strong magnet. And we talked about electromagnetic induction in the last video, so we know if you turn a loop of wire through a magnetic field, then you get electricity, and then you can send that electricity to people's houses and stuff. Okay, so that's basically how a fossil fuel power station works. And this is essentially the same thing with a nicer picture and a Sankey diagram. And notice that at different stages in the process, you lose some energy due to different, aspects. Obviously, some chemical energy, as energy goes into the hot steam, you lose some energy there. As the hot steam is pushing on the turbines and creating kinetic energy, there's friction in the turbines, of course, and so you lose some thermal energy there. And also, as the generator is spinning, there's some energy loss there. And so fossil fuel power stations tend to have an efficiency somewhere between 30, I'd say 30 and 50% ish. Okay, natural gas tends to be more efficient than coal, but generally speaking, these power plants are not more than 50% efficient ish. Okay, this is basically the same thing except with natural gas. Okay, so this is 50%. The other one said 40%, but somewhere in the 30 to 50% range. You do need to know that natural gas is more efficient than coal, because that is a fact that you should know. Okay, and the last thing to talk about in this video is just really briefly talking about natural gas. So natural gas, when we talk about natural gas, what we're really talking about is a mixture of gases. Okay, so mostly methane, but also probably some other elements like carbon dioxide, nitrogen, hydrogen sulfide, helium. And when you burn natural gas, it produces carbon dioxide, which is a greenhouse gas, but it produces less carbon dioxide than coal, which makes it quote unquote better for the environment. Okay, so which is true, it is better for the environment in the sense that it produces less greenhouse gases. And so if we want to, keep using fossil fuels, but we want to try to, be more environmentally friendly, then one thing we would try to do is transition from coal to natural gas, um, which we've been doing over the past couple of years, which is good. Okay, and again, this is the same natural gas that people, if you have it like a gas cook stove, or like a water heater is powered by gas, or like your furnace is powered by gas. Um, that's the same type of natural gas. This natural gas is actually colorless, odorless, and tasteless, and so the people who do the natural gas actually add a chemical into the gas to give it kind of a stinky smell, so that way if you have a gas leak in your home, you can smell it and you can like, leave the house or whatever, I don't know, call 911 or call the gas company or something if you ever smell gas in your home. But they actually do add that chemical in just to give it that smell. And then just really briefly, I want to kind of mention, let's see, coal. We already talked about coal. We talked about the transportation requirements of coal. This is kind of a crazy fact that 25% of the cost of coal is just to cover the high transportation costs. Because you have to have like each power plant has to have like hundreds of tons of this like shipped every day, hundreds of train cars just filled with coal, taking the coal to the um, the power plant just to like throw it in the furnace and burn it. And the cost to run those trains is like 25% of the cost right there. So there are, of course, significant disadvantages to using coal as an energy source, but we also talked about the advantages in the last video, especially for third world countries, because of how abundant coal is, how easy it is to use, how you don't require a ton of like advanced technologies to do it. You just, throw it in the furnace and it goes. Okay, but that's kind of a crazy fact right there. The last thing I briefly want to mention in this video is about fracking. I'm going to link some videos about fracking um, just so you can be informed about what that is, but because that's something that a lot of people like hear about in the news and they have opinions about it, so I kind of want to share some of that information with you. So I will link some videos about fracking so you can watch those. All right, so based off of everything we've talked about, I want you to outline some advantages and disadvantages of fossil fuels. Um, so go ahead and do that now. All right, and so we're going to go ahead and stop here, but in the next video, I want to talk more about nuclear power and the advantages and disadvantages of nuclear power compared to fossil fuels. Because besides fossil fuels and nuclear power, basically we have renewables, but the renewables that we'll talk about at the end of this unit all have their own issues, as we will see. Okay, so we'll talk more about nuclear power in the next video. As always, please let me know if you have any questions, and I'll see you guys in the next video.